Okay, great. Thanks everyone for joining us. Very excited to have you here and very excited to do this very first webinar from QuEra Computing. We're very excited. We've had a very good month here where we've just put up our very first quantum computing device up onto the cloud online. No doubt that's why a lot of you are joining us today to hear how to use that device, which today we'll talk about how to use that device for quantum simulation. Of course, it's good for a lot of different things. Next week, we'll talk about quantum optimization as well. But we're very glad that you can join us today. So my name is Nate Gemelke. I am the Chief Technology Officer at QuEra Computing. I am actually one of the co-founders of the company, and I joined QuEra after a long history of doing quantum simulation professionally. My last job was as a university professor. We have built a machine here that is at least for me the ultimate dream in being able to use commercial devices to really do cutting edge research and also start to explore the territory of quantum simulation with neutral atoms. I'm joined today by our senior scientist at QuEra Computing, Dr. Al Lukin. Dr. Lukin is one of the driving forces behind putting our new device, Aquila, up online for you today. Alex joined us after a very successful career, getting a PhD at Harvard, also doing quantum simulation, looking at things like many-body quantum dynamics, entanglement, and optics. He also is an expert in some of the hardware that we develop, having done a postdoc working on integrated photonics at MIT. Okay, so just a quick overview of the agenda for today. We're going to try to avoid talking too much today. We're going to give you a very quick introduction to QuEra and the Aquila device. We're going to spend just 5 minutes doing that before we tell you the basics of quantum computation using Rydberg atoms. So we'll spend about 15 minutes doing that. And then I think what most of you are probably here for is we will actually do a demo on the Aquila device itself. So we'll take about 30 minutes to walk you through some of the easiest use cases that you might explore using the Aquila device. And then at the end, as promised, we'll answer some of the questions that you put in the Q&A section for us to answer. So we'll come around to that at the end of the talk, maybe give you about 10 minutes for questions. Okay, so QuEra Computing was founded about 3 years ago and built on a very strong scientific foundation. So the founding team actually included some of the luminaries in the field of quantum computing, especially with neutral atoms and with Rydberg atoms. And so that includes Misha Lukin, who's a professor of physics at Harvard University. Also Marcus Greiner, one of the MacArthur Genius Grant Fellows and also the inventor of the quantum gas microscope. Vladan Vuletic, who is a pioneer in creating large entangled quantum systems, especially with neutral atoms. And then also at MIT, Dirk England, who is an expert in using integrated photonics to control quantum systems like atoms. So in addition to that founding team, we also have Alex Kiesling as our CEO. As a graduate student, Alex actually worked in the group of Misha Lukin to create the first device very much like the Aquila device that we'll be talking about today. So in addition to that, I joined the team as a co-founder and also the CTO of the company. So QuEra itself is actually made up of a lot of people. We're about 40 people right now that work on all of the different aspects of bringing a quantum computer to market. And that goes not just at the hardware level, but all the way up to the algorithmic level, stopping at software in between, helping you actually craft those algorithms and deploy them on the hardware. So we're a truly integrated company. And I think this is important because the device that we'll be talking about today is a little bit of a non-standard device. We call it a quantum simulator. It lets you explore lots of things. It's not a gate-based computer per se. And for that reason, some of the algorithms you might think of as kind of non-standard algorithms. It lets you do a lot of things really well. For example, simulate quantum spin liquids using Rydberg blockade physics, things like that. Now, to help you design algorithms and explore applications on this device, we have built numerous software tools to help you do that. One of the most important is a very sophisticated emulation tool that will let you actually simulate what happens on the quantum computer with relatively large numbers of atoms. So this is a whole software package called Blockade. It's an open source project. So actually, if you want to log into the website for Blockade and even contribute to the code development yourself, use it, really understand how it works on the insides, you can do that through that open source project. But of course, what we're all here for today is actually the hardware at the bottom of the stack. And so we are building some of the largest and most flexible quantum hardware using neutral atoms today. And that's what we want to talk about, is what you can do with that machine. So where does it come from? That's a great way of understanding what it can do. So I want to take you back just very quickly into the prehistory of the Aquila device. Actually, it's built off of a series of academic breakthroughs that started in the Harvard laboratories that QuEra's spun out of. So if you go back to November of 2017, actually, you'll see one of the largest quantum computers at the time, built out of 51 qubits, sitting in the Harvard laboratory. So that was kind of the impetus and the inspiration for founding QuEra Computing. So we spun that off in July of 2019. By July of 2021, that academic research group at Harvard had demonstrated the first control over 256 atoms. By that time, we were positioning those atoms in real time in 2 dimensions. And that enabled in December of 2021 simulation of quantum spin liquids. So that's a big breakthrough, right? That's something that people had talked about for decades, but never really found a good physical realization in nature for it. So we actually just built it with the kind of device that you'll see here today. By February of 2022, we were demonstrating scaling advantage for optimization problems over the classical benchmarks on the same types of problems. So this happened for the independent set problem. So that led us to what we're all here for today. In this month, we have launched now our first device, which is very similar to the Harvard device that begat all of these kinds of breakthroughs. And it's now available to you. You can log into Amazon's Blockade service and access our device and start programming it. And we'll spend the rest of the webinar today showing you exactly how you can access that device and how you can program it and do fantastic things of your own design with that machine. Okay, so Aquila itself, what does it look like? Well, here's a picture. Actually, this is physically what it looks like. This is an actual picture of the device. This is a very powerful quantum processor. You can access 256 entangled neutral atom qubits through this machine. You can keep them coherent through computations. The architecture, like I said, it's not a gate-based computer, so it requires a little bit of specialized knowledge, and that's what we're here to learn today. It works in an analog operation mode. We like to think of the power of this machine really being in how flexible it is to move the atoms around and put them into different kinds of geometries. So a good phrase for that is that we have field programmable qubit arrays in this device that we can use. Now, this is important too as time goes on. We have built this machine with a very modular architecture. And what that allows us to do is really upgrade this machine periodically. So you will see as time goes on, we will be rolling out new features into this Aquila device to allow you to do other kinds of things. And we'll come back to that at the very end of the webinar to let you know some of the things that we have on the near-term schedule. Okay, so what can you do with Aquila? One of the big areas that you can explore with Aquila that is really useful right now, today for scientific applications is to do Hamiltonian simulation. So you can use this device to explore equilibrium quantum phases of matter, non-equilibrium quantum dynamics by basically whacking the system and seeing how it evolves in real time. You can also look at thermalization effects through that device, and you can build very exotic types of things like lattice gauge theories and explore how they work. It's not just for science problems that you can use this device either. It's also for real world problems in things like logistics as well. So a good area there is optimization problems. So if you have a big network analysis problem, you really have to crunch a lot of data in a graph. This is a good device for that. You can calculate a lot of properties of graphs like maximum independent sets, maximum cliques, minimum vertex covers, dominating sets, even do graph coloring problems with devices like this. We will add a few features in the near term that also will allow us to do other things like variations of those problems, like the maximum independent set problem, and also QUBO problems. But we are excited that there are other kinds of applications in the near-term future for these devices as well. And we would very much like to see exploration of machine learning problems using this platform as well. So there are a lot of different modalities that you can actually exploit for designing algorithms in the system as well. You can do adiabatic protocols, very good for producing equilibrium phases of matter, for instance, quench dynamics, variational quantum algorithms, related things like QAOA, quantum approximate optimization algorithms, and also explore things like quantum sampling, all with the same device. So that is a very rapid kind of introduction to not just the Aquila device, but also QuEra computing. But I'm going to hand it over to Alex Lukin to take us through a real tour of all the innards of this machine and help you get started accessing and using the Aquila device to do all of the things that you can dream of with the machine.
Thank you, Nate. So I'd like to start with giving you a quick preview of how Aquila works under the hood. So we have a neutral atom processor, and in order to assemble it, we shine a lot of focused laser beams into the vacuum that has still some atoms of rubidium floating around. And as long as these rubidium atoms go near the focus of these laser beams, it can get trapped. And we can use those atoms for quantum information processing afterwards. So first thing we do is actually we take the image, and here you have an example image from our machine, where each bright dot corresponds to a single rubidium atom loaded into optical tweezer. So in order to do quantum information processing, we need to have a qubit. And for these purposes, we will use the qubit consistent of the ground state and the Rydberg state. We can apply a laser drive that will drive our qubit between those two levels. As a user, you will be able to tailor this drive to whatever applications you have. So these excited Rydberg states are actually very special. Their main property is that they have a different interaction strengths depending on the distance between the atoms. So let me illustrate this. Let's imagine that we have two atoms that are spaced far apart from one another. In this case, if I try to drive them to the Rydberg state simultaneously, they will be allowed to do so. However, the story is different if the atoms are placed close to one another. Here, the effect called Rydberg blockade kicks in, and now if I try to drive the system, only one of them will be allowed to excite it into the Rydberg at a time. And the energy for exciting the second one will be highly lifted for this case. And this really allows us to engineer interactions in a system by positioning qubits at different distances from one another. So how can we do this? And we can achieve this by implementing this so-called field programming qubit array architecture. And what it means that for each run of the quantum processor, you as a user will be able to define the qubit arrangements and hence the interactions in the system. And let me just give you a quick preview how can it look like. So for example, here you can create a register with 256 qubits on the square grid. However, we're not limited to the square grids. We can also create something like a Kagame lattice that will allow us to explore different physics. Or we can even go as much as put these atoms in the arbitrary positions, here outlining the world map, which might be useful for your application. And one thing that I really want to stress is that this can happen really on each run of the experiment. So here you can see an animation where each the frames of this animation is the new realization of our processor. So you can kind of see the flexibility of the platform we have. And that's, we think, will allow you as a user to really explore these exotic phases that you can prepare, as well as being really easy to encode a new algorithm that you can come up with, as well as minimize the time between the iterations of the algorithms. So today, we're going to be focus our webinar on analog quantum simulation, and this protocol will be mainly focused around the Ising Hamiltonian of such type. So let's look at the terms in this Hamiltonian. So first terms correspond to the energy shift of neighboring atoms due to the Rydberg blockade mechanism that we've seen. And as a user, you will be able to adjust this term by varying the positions on the atoms in a 2D plane. The second term corresponds to a coherent drive, where you can control both the amplitude of the drive as well as the phase as a function of time during your quantum simulation. And last term is corresponds to an energy cost for Rydberg excitation on each side. And maybe some of you will be familiar with it in a concept of the chemical potential in the system. And we can introduce it by simply detuning the driving laser frequency from the qubit resonance. So in our example today, we're going to be talking about adiabatic state preparation. In order to do so, we first need to come up with a way how to start with our initial state of the register, which consists of all the atoms in the ground state and connect it to some ground state of this Hamiltonian. And we can do it by changing this eigengeometry excitation called delta. So if you notice, if this delta is large and negative and dominates the dynamics of the Hamiltonian, then ground state of H is actually all the atoms in the ground state, which is our initial state. So now if I look on the other side, when delta is large and positive, the atoms would actually be like to be promoted into the Rydberg state. So now if I tune delta from large negative to large positive, I should be able to promote all my register into the Rydberg state, unless there is an energy penalty constraint given by this interaction term. And so let's focus on it, focus on this term a little closer. So if we plot the interaction energy as a function of distance, you will find that at large distances, the interaction energy is pretty much negligible, but at some scale that we called Rydberg blockade radius, it will kick in and go up very fast, which means that you can kind of think about this term in this simple way of if the atoms are within the blockade radius, only one atom out of this group will be able to be excited to the Rydberg state, whereas if the atoms are separated larger than blockade radius, all the atoms will be simultaneously able to excite to the Rydberg state. And let us illustrate this on this example of the 3x3 register. When we first consider the atoms spaced far apart from one another, and now if we try to sweep the tuning from large negative to large positive, all of them will be able to be excited into the Rydberg state. However, the situation is different if we now prepare the same register at smaller spacings, such that the distance between neighboring atoms will be within the blockade radius, but the distance between next nearest neighbor will be outside of the blockade radius. So now if we do the same adiabatic sweep, we can see that only some parts of the atoms will be able to excite in a Rydberg state, realizing so-called the checkerboard phase in this scenario. So this is something that we would like to see today in our demonstration example. So let me just also kind of tease you a little bit of like what these analog quantum simulators are good for. And just by kind of looking at the recent years scientific publication, such devices were able to study multiple phases of matter in 2 dimensions, as well as the critical behavior at their phase transitions. Also, as Nate already mentioned before, there was first realization of quantum spin liquid, a state of matter that was theorized for a long time, but no physical system was able to implement. And this state is actually very interesting because it's one of the ground states that possesses a large amount of entanglement, and it could be also suitable for quantum information processing. But we are not only limited with this device to studying ground states. We, in fact, can also study the quantum dynamics of the system far out of equilibrium. And one example could be the scarring behavior after the quench that was also demonstrated in a Harvard experiment previously. So now let's quickly take a look how would one program the Aquila. So each program will basically consist of three main steps. First, we will be defining our qubit register that will host our quantum simulation. Then we will define the drive that we want. And last part is we'll be running the simulation on the device and analyzing the data. And with this, I would like to switch gears. So once you log into the Amazon Bracket account, you will see a dashboard like this. And here on the left, there are a few useful tabs that you can see. So first of all, we can look at devices. And here you can see the availability of every device available on the AWS. And here is the QuEra's device Aquila. And you can see when the next availability window starts. And for now, we are available to customers on Tuesdays, Wednesdays, and Thursdays. Now, on the top of notebooks, you can find your work notebooks that you can use with Aquila. And so let's open one of them and see how this looks like. So today in this example, we would like to do two things. First, get you familiar with the way you would specify your program on Aquila, as well as show you how by tuning the distance between the atoms, you can introduce interactions in your system. So let's start with that. So let's start by running some helper functions. And our first example would be to try to see the non-interacting 3x3 lattice that we can drive into the Rydberg state. So in order to start your program, we would like to create a new atom arrangement. And you can do so by calling the atom arrangement function from bracket AHS library. And here I will define a helper function that will allow me to make square lattices with the given spacing. So one useful tool that we have is the device capabilities that you can pull from AWS device. So in order to do so, we need to define a QPU object in this way, and then call the properties on it in order to get the capabilities. And since now we're trying to create a register first, let's look at our lattice capabilities of Aquila. So if we run this, we will learn that we have a user area of 76 micron height and 75 micron width available for your qubit placement. Total number of qubits should not exceed 256, and some constraints on the positioning of the qubits. So now let's move on to create our first qubit register, which is spaced far apart, larger than blockade radius, in order to realize non-interacting qubit arrays. So for this, let's define a lattice, 3x3 lattice with 15.7 micron spacing that we can do in this way. Also, let me mention a useful utility called show register from AHS utils that allows you to visualize the register that you created, as well as it enumerates the qubits in order for you to make sense of the results that will come back from the device. So now you can see that we created a 3x3 lattice spaced as we wanted by 15.7 micron. So now let's move on to the next part of our programming, namely creating a drive. And again, let's start with looking at the Aquila capabilities of the Rydberg drive. The notable things that you might find useful is the detuning range, as well as the maximal Rabi frequency that's available for you. and note that these values are given in radians per second. So, right, so once we know those numbers, we can move on to create our piecewise linear ramp. So what we would like to do in our quantum, in our simulation example is ramp up the Rabi frequency to its maximum and hold it constant. In the meantime, we can ramp the detuning from a large negative value to a large positive value simply linearly and keep the phase of the drives constant throughout the evolution. In order to do so, you can use the get drive and show global drive functions from AHS utils, which you can now just write down your piecewise linear waveform in the following way. So now it's time to create an analog Hamiltonian simulation program using analog Hamiltonian simulation function from bracket AHS, and we do so by passing it the register that we created as well as the drive. So one useful feature that Amazon gives you is ability to run your quantum program simulated classically on a computer using the local simulator. Of course, that's only worked for the problem with the small number of qubits, but for our example, we actually can do so. So let's see how that works. In order to do so, we can import the local simulator from bracket devices and define QPU simulator in the following way. So now we can run the simulator and have a small helper function that will allow us to retrieve the results of the simulation. And now once the simulation is done, we can actually visualize our result by looking at the plot average density 2D function, again from AHS utils. And so one quick note on the way you will receive the results from Aquila. So you receive results as a string of zeros and ones corresponding to a ground state if the result is 1, and for Rydberg state the corresponding result is 0. However, usually for our purposes, it's nicer to look at the Rydberg population density, so we'll just redefine Rydberg density as 1 minus the results. So now if I visualize the result of our classical simulation, we see that it predicts that by the end of our run, all the qubits should go into the Rydberg state. That's what we expect. And now let's try to run the same program on Aquila. In order to do so, we again need to make the QPU object from AWS devices and submit a job to the QPU by running qpu.run, passing it the analog simulation function as well as required number of shots, and collecting results by using the .results command. So typically such a program will take about 5 to 10 minutes to run on our device. And here, for the sake of time, we have pre-computed one of the runs like this, and now we can just visualize what the machine will do at the end of the computation. So let's visualize the results from the machine. And indeed, as we expected from our simulations, all the atoms were able to be promoted into the Rydberg state. So now let's try to introduce the interactions in our system. And as we've seen before, the way to do it is simply by shrinking the distances between the atoms. And we want it to be such that the nearest neighbors will be blockaded, but next nearest neighbors will not. And the good spacing of the lattice for this purpose would be about 6.7 microns. So first, let's create our 3x3 register at this spacing. And here it is visualized for you using the show register function. And now let's again try to run the same task on Aquila, but now with this closer register. So if I pull up the results that we have pre-run for this demo, we can see that now only half of the atoms were able to promote into the Rydberg state. And the atoms on this diamond were blockaded from excitation. And that's an example how we can, by tuning the distance between the atoms, we can tune our system from a trivial phase when everything goes into the Rydberg into the ordered state when only a subset of the atoms are allowed to be excited into the Rydberg state. So now you might ask yourself, what's the best way to utilize all this number of qubits that Aquila can offer? And you can do it in two different ways. One, you can parallelize your computation by creating a multiple registers of the same program such that these registers are disconnected from one another. And the other, of course, more exciting thing to do is actually go to a much larger system that you're no longer will be able to explore classically. In this case, let's see these two examples in action. So first, let's start with creating a parallel register. In order to do so, we first find out the footprint of our single register, and then by using the capabilities of the device, we can figure out how many registers will fit. But remember, we would like these registers to be independent, so we would like to make the distance between the register to be larger than blockade, and here we're picking something 11.5 micron. That should be safe for what we want to do. So running this, we can see that our capabilities will allow us to create 3x3 grid of 3x3 registers. And let's now try to do so. So if we now run this cell, it will create us 9 registers that now span most of the available field of view of Aquila. And then now, if I try to run the adiabatic protocol on such a register, I would expect that each of these 3x3 registers will independently go into the checkerboard phase. So let's see what the Aquila result would look like. And indeed, what we see that if we do these parallel registers, each one of them actually is going into the checkerboard phase independently of one another. So now let's see if we can do a simulation of a larger system. For that, we simply will try to eliminate these gaps and prepare a large 9x9 system that is all spaced by 6.7 microns. In order to do this, we will use our lattice function and create this register. That's how it's going to look like for us. And now we will submit this task to the QPU. As a result, we will see now this large checkerboard phase where every other atom is promoted into the Rydberg state, and the rest of the atoms are left in the ground state, indicated by these results. So, and that concludes my today's demonstration. And just before I hand things over back to Nate, I would like to summarize what we have seen today in this demo. So we have seen how to program and interact with the device, as well as how to use flexible lattice geometry to introduce interactions in the system and change the quantum dynamics in the system to arrive to different phases at the end of our simulations. And with that, I'd like to pass it to Nate in order to do some final remarks. Thank you so much.
Okay, great. Thank you very much, Alex, for that very thorough introduction into how to use the machine. I do want to add a few things. We've talked today a lot about what Aquila can do for you right now. But I do want to point out that we are introducing new features to this machine and upgrading it. And you will see these things roll out on a schedule. So we do want you to know that we will be enabling digital, analog, and even hybrid quantum computing all in this type of machine. We're going to do that without rebuilding the machine itself. So you'll actually see rapid progress on all of these fronts. Some of the upcoming features that we do have planned certainly will help you implement more Hamiltonians with different kinds of features in the machine itself. Also allow you to access more qubits. I saw during the Q&A that we had an answer, what limits the number of qubits that we can work with. We'll answer that in just a minute. We also will be adding features that characteristically change how the device is used. One of these will be to introduce local detunings, which is to say that on that Rydberg transition, you'll be able to go in and access individual qubits resonance for that transition to the Rydberg state. We will also be introducing a degree of local control, meaning individual control over those qubits rather than the global control that you've seen today. As time goes on, we are moving this platform more and more towards the ultimate goal of fault-tolerant universal quantum processing. And to do that, we will be adding features that will enable you, for example, to create different zones with quantum memories in them, even be able to implement error correction schemes. So all of these things are in the near to midterm future for Aquila and for devices like it. We are also building new machines as we speak. So you'll see these coming online shortly. So I do want to give us time to answer some of the questions that came up in the Q&A chat. And I think the way that I'll do this is I think that we handled a lot of them with our crack team of scientists that got in and answered them in the Q&A chat itself. But I do want to call out a few of these questions because I think that they're really great questions, and it might benefit everybody in the webinar to hear the answers to some of these things. Well, we've got people like Alex on the line. So the first question that I wanted to call out came from Lindsay. Lindsay was asking, what limits the size of arrays you can achieve? Is it the vacuum performance? Is it sorting time? How big of an array can you get to? And I'm going to hand that one off to Alex.
Thank you, Nate. That's a great question. So currently, our arrays are limited by some technical problems, such as like laser power, such that we also have plans to increase. So our sorting probable fidelities, I think, are also given in capabilities, so you can look them up. And that's basically, I think that's the answer.
Okay, great. I think we also have another question from Dong that I thought was worth just kind of calling out and talking about, not just what we can do now, but also this near future, kind of to the point of the previous slide. Dong is asking, can Aquila do fast atom shuffling?
Yeah, so currently you only can change the geometry of your processor for each task, and during the evolution, it's not available right now. But as we kind of mentioned, it's something that we really would like to add into Aquila in the near future. So stay tuned. This feature should be available sometime soon.
Yeah, and I do also want to call out that our academic colleagues down the street at Harvard have demonstrated the ability to move atoms in real time and preserve the quantum information. So this is something that we're very excited at QuEra. We are thinking every day about how to get these into the machine, and we will have news for you in the near future about adding that ability to do that. I did want to call out another question came from Richard. He's asking, does the processor allow the interaction between arbitrary qubits, or is there some kind of constraint from topology that prevents you from having all the qubits talk to each other?
So that's a great question. So basically, the way the qubits interact, they interact through this Rydberg blockade mechanism, which has very steep spatial dependence. So everything within about 8 to 10 micron radius you can make interacting. However, things that's further apart than about 15 microns are generally would be non-interacting in the processor. So depending how many qubits you can kind of pack in within this blockade radius, those will be the qubits that will be strongly interacting with one another, and everything outside of this blockade radius will be generally non-interacting. But one thing I would highlight here is that this blockade picture is a little bit simplistic, and you really should look up how the kind of interaction scales as a function of distance, because, you know, for your quantum simulations, it actually might become relevant tuning parameter that you can tune to arrive at different phases of matter, for example.
Another good question from Don. He's asking, what would the estimated runtime be in Aquila for a typical simulation task with about 200 atoms? Would it be several hours or a day? And what is the scaling behavior of runtime with the system size?
So that's a great question also. So the main advantage of Aquila is that the runtime is independent of how many atoms you would like to have in your processor. So if you want 1 atom or you want 256 atoms, the runtime would be exactly the same. What matters is how many shots you want to do to average your results. And that's, you know, to give you a perspective of scale now, it takes about 5 to 10 minutes to run about 1,000 shots of your program.
So I do want to say that there are quite a few things that you can join us for coming up. In fact, this webinar is just the first of 2. We will have another webinar next week. It will not be on the same topic. In fact, we'll talk about something else. We'll talk about solving optimization problems using the Aquila device as well. So you can join us same time, same day of the week, Monday, November 21st at noon Eastern Standard Time. If you want to register in advance for that, you can register at www.QuEra.com. Now, we also think that it's pretty important for you to be able to just get on the phone with our staff scientists and talk through the problems that you're interested in. We will have an office hour coming up for technical discussions to help you through any of the problems that you might have encountered along the way, accessing the machine or doing the things like what Alex showed you today, or things that you came up with on your own and just had trouble implementing. You can join us for that office hour. That will be Monday, November 28th, also at noon Eastern Standard Time. And again, you can register on our website in advance if you'd like to. We'll make sure that we have a range of people on the phone for you. So if your question really involves hardware, software, whatever it is, we'll be able to answer that question. But most importantly, we would really love for you to try Aquila for yourself. So you can log in online, do the things that Alex showed you today, play with that machine to your heart's content. We also would encourage you to go to AWS's site and apply for free research credits for some of the things that you want to do. You can use this QR code here, or you can type in the web address that's here. Also, the demo notebook that you saw today that Alex went through is also available at the address at the bottom of your screen. So if you're ever interested in going back and repeating those steps, no problem, you can look it up there. You can also get in touch with us anytime that you want to ask any question that you need to at info@QuEra.com. We'll have somebody get back to you as soon as we possibly can. Any question that you want to ask there, we will try to get that answer to you as quickly as possible. Okay, so thank you very much for joining us, and please join us at these future events.